Okay, welcome, welcome, welcome. We're going to be going through a few of the most commonly asked questions in Math 111 this morning. So the first problem I have for you to discuss is the phone number problem. So always get lots of questions about this. If you're watching this video and you'd like to skip ahead, the other two problems that we'll be discussing are the bug on the pentagon, and the last problem that we'll discuss is a problem on strong induction. So zoom ahead if you want to listen to those. For now, we'll talk about the phone number. So we have telephone numbers. So your number could be like 000, all zeros, or a bunch of nines, or anything in between. And this time, when a number like that is called, there's a vertical switch going on. So 1 and 4 could make a change, or 6 and 9 could make a change, or possibly 8 and 0 could also be in a change. So then, to deal with this error, we've decided to add a 6-digit. In coding theory, we call this a check digit. So this check digit is going to get added in some proposed scenarios, in some different possible codes 1 to 4. And our job in this question is to decide if these codes can successfully detect, or maybe not detect, this error. So what do we mean by successfully detect? So let's just think about code 1 for a moment. So if we have this code and we're able to detect an error, so what does that mean? It means that that congruency would change from being a true congruence. So the congruence changes to being not congruent. That's when we would say we detect the error. It can only do a true or false thing. So if the congruence is true, and then all of a sudden it's false, then it says, hey, this phone number is no, I'm not going to let this through my system. So we would not detect if the congruence was still true, even though an error has occurred. So let's think about some of the errors that might occur, or the change that would take place if an error occurred. So let's just say A. A is going to represent the first digit in our phone number. If your first digit is 0 or first digit is 9, anything in between, that could be an A value. So let's say that we have an error, and it's changed A to, let's say, A prime. So A prime specifically is the error, and A is your first digit of your telephone number that you begin with. Okay, so what's important here is the change that occurs. So how much did A increase or maybe decrease to become A prime? So I'm going to write the change caused by the error. Let's call this C for change. And what does this C equal? I'm just going to say it's the difference, the difference between A and A prime. And it'll be different in different scenarios down here. So that's really the key to decide if we can have a successful detection of a vertical error. So which of the above codes are successful? And there's a little note here. Let's just read it in detail. It says, note, all phone numbers from 000 to 999 need to be assigned a check digit in order for the code to be successful in error detection. Okay, so we'll come back to that note, that all of the X values here need to be legitimate, and we need to assign them to all of the phone numbers. Okay, so code 1. Let's start there. We're going to keep looking at this C value, this change. So A minus A prime, what could that possibly be? So looking back at our number pad here, remember we said there's digit errors that swap vertically. So you could have a increase by 3. It could go plus 3. But it could also go minus 3 if the 9 changed to the 6. So plus or minus 3. And then I suppose with 8, it could go up or down there as well. So you could get plus or minus 8. And for a successful detection, we would like in mod 4 to be able to notice that difference. Now for plus or minus 3, we would notice that, but plus or minus 8 is unfortunately 0 in mod 4. So the 3 here is not a problem, but the 8 causes some problems. So if you had a phone number that had a digit of 8 and the 8 changed to a 0, you're not going to be able to notice that detection in mod 4. It's not going to change anything. So what you can do in this case is just come up with a counterexample. Let's say my phone number is, let's keep it simple, all zeros. So we have 5 zeros, and then we would assign a corresponding X value of 0 to my phone number, which would be 0 itself to make that congruence true. And let's say, unfortunately, we've had a digit error. So an 8 gets swapped out for the 0. So we had that type of error occur. And the check digit just carries along with the erroneous code word. But unfortunately, the system doesn't detect this. It says, hey, this phone number is good. You could have a number of all zeros in this code, and someone else could have the number of 8 and then all zeros. So they're both valid, and that's not what we want. We want a valid phone number anytime the error occurs to change to something invalid. So code 1 cannot detect the error. So there's a little fill in the blank, can circle the successful code or codes, and 1 is not successful. Okay, so let's move on to code 2. So code 2 will be analyzed in a similar way. Again, we'll look at this C value. So A minus A prime is again those values, plus or minus 3, plus or minus 8. Those are all the changes that occur, right? C is this change caused by the error. But this time, we're working in mod 6. So let's think about the different possibilities that you could get when you divide such integers by 6. What remainders could we get? So if it's plus 3, you could get 3, or minus 3 is also 3 in mod 6. Or 8 is either 2, or minus 8 is 4. So it could be 2, 3, or 4. And that's good news for detection because none of these are congruent to 0. So we have this detection situation where if the A changes, or any of the other letters, it doesn't really matter if it's A, in such a manner by this vertical error, the system will detect it because the congruence will be true and then change to a false congruence. And it'll say, hey, this phone number is no longer good. Please try to dial the number again. So we get error detection successfully. So code 2 works out. So finally, let's move on to code 3. And I guess both code 3 and 4 are done in mod 9. And they're similar in that they alternate the coefficient of 2 and then a coefficient of 1, 2, 1. And code 4 does the same thing. So let's just chunk those ones together. So code 3 and code 4, we can analyze those together. Now, I suppose there is one difference, even though they're both in mod 9. Let's remember this note here, that all phone numbers need to be assigned an X value. So we do need to make sure that we can find an X no matter what the A, B, C, D, E is. So that's no problem for code 3. For code 3, you just say, okay, we can find the X by moving all of these to the other side and solving in mod 9, and we get our X value. So you'd have to do the same thing with code 4 and the same thing with all the other codes. And code 4 has a little bit of a wrinkle because the X is being multiplied by 2. So to solve, you would take all of this, you would move it to the other side, and then you would try to solve for X. And because in this case, our 2 is invertible in mod 9, we don't have any issue here. You can solve for X by just multiplying by the multiplicative inverse of 2. So there's no issue with this note. However, if this was 3, then there could be an issue there because there would be some X values that maybe wouldn't have solutions, and every single phone number needs to get an X value. So if that number was 3, we'd say we got to throw code 4 out. It's not a good system. It's no good if you show up at the check digit assigning location and they plug it into code 4 and they say, hey, I can't come up with an X value for you. Okay, but in this situation, code 3 and 4 can be treated in a very similar way. We can chunk them together. There's no issues that come up. Okay, so with this situation, we have one more wrinkle. There's a different type of error that could occur. Either the error could occur on the digit itself or a digit that's being multiplied by 2. So let's think about those two situations with our change. And I'll just say C1 is one possible change that could occur. And again, with A minus A prime with no coefficients. You could get plus or minus 3, plus or minus 8. So this is exactly the same as what's above. But this time we're working in mod 9. So maybe just above I should write, but this time our congruent symbols were in mod 6, and now below they'll be in mod 9. So if we think about all the possibilities there, you could get a 1, you could get a 3, you could get a 6, or you could get an 8. Again, none of those are congruent to 0 in mod 9. So there's no issue with the first type of change that could occur for code 3 and 4. So we get successful detection. And now we'll think about the other type of change that could occur. You could also get twice A changing to twice A prime, right, for that type of situation. And it could be with any of the other letters as well. We're just using A as an example. We don't need to repeat the same procedure for B, C, D, E. It's the same. Okay, so this time around, let's think about all the possibilities that you could get. So it's really just twice of everything that's above. So the 1 could become a 2, the 3, that could become 6, or 12, or 8 multiplied by 2 is 16. So it could be those possibilities in mod 9. And we should reduce those just so we can see the remainder. Or we can just maybe notice that none of these are 0 or 9 or 18. So these are also not congruent to 0. So again, we get successful error detection for codes 3 and 4. So the only one that didn't work out this time was code 1. So that is the vertical error for a phone number problem example. Okay, so our next problem that we're going to discuss is the frog on the octagon problem. So a frog starts jumping from vertex A, and from any vertex on the octagon, it will keep jumping except for vertex E. So once it gets to vertex E, it's stuck there, it stays there, it stops jumping around. So we're going to let A sub n be the number of distinct paths, so the number of different choices the frog has, jumping from vertex to vertex, landing at vertex E. And we'll do a similar thing for all of the other vertices. So if we just suppose that the frog is at vertex B, we'll think about the same situation. So the same idea where the frog can bounce around on these vertices however they like, but once they get to E, they stop. And same thing for every other vertex. We'll define a sequence by its letter. So D sub n, same thing. So it wants to calculate the first 10 terms of the sequence A sub n. And in order to do that, I don't want to count this step by step, have to sort of brutally go through all this counting process. It wants to go all the way up to 10, but we will do some of the counting. Like if we just have one move, there's no way that we can get to E. So there's 0 paths that will travel to E. If we have 2 moves, well, we could go back to A, or you could go to C, but still there's 0 paths. With 3 moves, there's still not enough to get all the way to vertex E. But as soon as you have 4 moves, at least there's something interesting. With 4 moves, you could go one way around or the other way around, to get yourself to vertex E. But after this, things start getting a little bit more complicated, because once you start traveling, you can't hit E before you use all of your moves, because A sub 5 says use 5 moves landing at E for the first time, or once you're at E, you're stuck, you stay there. So it starts getting a little bit more complicated, and this is where recurrence relations really shine for us. If I can find a recurrence relation for A sub n, then I can start to count these numbers that are here in a little bit more of a reasonable way. Okay, so I'm going to just start by writing A sub n down on my page. And I want to get A sub n in terms of maybe smaller A values, A sub n minus 1, A sub n minus 4, something like that, to build my relationship. But I can't see a direct way to do that. But maybe we could start by saying the bug's first move is either to B. So you could add up all the ways of traveling from B to E, plus all of the ways of traveling from H to E. If you add all of those together with one less move, then you will get A sub n. That's another way to write A sub n. So let's just write over here that this is move number 1 that gives us that relationship. Either the frog goes that way or it goes that way. Okay, so the next thing that I want to think about here is some symmetry. If you're the frog and you're starting at B, compared to the frog and starting at H, and you want to count all the ways of traveling to E, there's some nice symmetry that's going on here. Let's just say you had 5 more moves, for example. From B, you could go 1, 2, 3, 4, 5. Or from H, you could go 1, 2, 3, 4, 5. And those patterns are symmetric. They're symmetric among a line of symmetry. Let's just draw that in from E to A, right? Things are symmetric over that line. So the B sequence is exactly the same as the H sequence. And G is the same as C, F is the same as D, we might not ever have to think about G and F at this point because we can just think of symmetry by working on one side of the line of symmetry. So A sub n can be written as B sub n minus 1 plus B sub n minus 1. And let's write this in red by our nice line of symmetry. So by symmetry. Okay, and then we can do ourselves one better and write this as twice B sub n minus 1. So that's a nice relationship to start out with. At least we've got A in terms of B. It's not really what we want to finish at, but it's a start. So let's think about, well, what does the frog do next? Well, from B, you could go back to A, or you could go to C. So this means that we could use one move and go back to A. So that's great. We have A written down on our page again. Or I guess, unfortunately, you could go to C as well, which is C sub n minus 2, because we've used two moves to get to C. So let's write in purple again. This is move number 2. Okay, so we're on our quest to write everything in terms of A. And right now we have A in terms of A and C. So we need to sort of get rid of the C. Okay, so what can we do next? Maybe let's think about move number 3. So from C, the frog either goes back to B or it goes to D. So we can write 2, A sub n minus 2. I don't need to mess with the A anymore. The A is really good. We're happy with it. The C can change to using 3 moves, going back to B, or using 3 moves and going towards D. Okay, so this is move number 3. There we go. So there's our move number 3. Sorry, a closed bracket in there. Okay, so this doesn't maybe seem like we got anywhere, but it is actually quite helpful. If we look back up on our page, we can write B in terms of A. We have a swap here. If we look at this equality, maybe if I call that equality star, and we think about maybe writing this equality out that we just wrote as twice A sub n minus 2 plus twice B sub n minus 3 plus twice D sub n minus 3. Notice that this equality star says that twice the B sequence gives me the A sequence, right? Twice the B sequence gives me the A sequence. So we can go ahead and use star to change it back to A's. That's what we want. We want everything in terms of A. So A sub n minus 2 plus twice the B sequence will give me one more in the A sequence. So it bumps back up to A sub n minus 2. So let's just maybe write brackets around that so we see the swap clearly. And this is by star. And we'll just copy the plus 2 D sub n minus 3. So that's really the only problem left is the D. Okay, now something else kind of interesting happens when the bug is at D, because most of the time when the bug is at D, right, if we think about our frog here at vertex D, trying to grab it there. So if I'm at D, most of the time I have to go back to C. You can go directly to E, but once you're there, you must stay there. So there's really just sort of one possibility by symmetry that could happen: 1, 2, 3, 4 moves to E. And if you're sitting at D and you have any more than 4 moves, you must go back to C. So let's think about what that means in terms of my equation below. I have twice a sub n minus 2, and maybe we can combine those, so I have 3 of those at the moment. And for D, you actually have to go back to C, as we just said, most of the time. And what does most of the time mean? Well, this D sub n minus 3 would change to C sub n minus 4 almost every single time. But we do need that condition of n is bigger than 4. When it's 4, that equality doesn't hold. You could go to E and things could be different. But every other time, you have to go from your D back to C. Okay, now we have A's and C's. Maybe we could look back above and try to think of a way of changing A's into C's. And there's our equation right there. Let's call this equation double star. So double star will allow us to swap C's back into A's, and you'll finish off the problem. So we have 3a sub n minus 2 plus twice C. Twice the C sequence is good because we have 2 times that. And then we just have to move this to the other side of the congruence. And we have to think about the indices. This indice here is the same, right, as that one. And the indice on the other side is 2 more. So, down below, we're starting at n minus 4. So 2 more than n minus 4 would be a n minus 2. And then we have to subtract because we have to move the other term to the other side. And that's the same indice. So subtract twice a sub n minus 4, right? Same indice and plus 2 in the indice. And we're all excited now, happy, jumping up and down. We've got a relationship that is all A's, right? 4a sub n minus 2 minus 2a sub n minus 4. And now we can go back to our chart at the top, and we can count these in a very reasonable mechanical way. So what it says is we look, to get like a sub 5, we would look 2 steps back and multiply by 4, and then look 4 steps back and multiply by 2 and subtract. So what we end up getting here is, I guess 4 times 0 minus 2 times 0, so that's still 0. And then what we would get right here for a sub 6, we would get 4 times 2, so that's 8, and then minus 2 times 0, which is just 0. Okay, and then I guess in this column, everything is 0, and we just look back for odd numbers in that column. So all the odd numbers are 0. And then right here, we would get 8 times 4 minus 2 times 2, so that's 28. And then maybe we get our calculator for the next one. We do 28 times 4, subtract 2 times 8. That is 96. And you could keep going and going. Okay, so that gives you a good example of how we can use recurrence relations to our advantage. This technically here with this relationship and these conditions here, you would need 4 of the conditions to complete your recurrence relation, right? That recurrence relation certainly makes it easier to count a sub 10. If we had to sort of go through the brutal process of thinking about all different ways you could move with 10 times and come up with 96 different ways, but here just by hand, just some pen and paper can cleverly calculate what these numbers are, and we could keep going bigger and bigger and bigger. Remember, you need 4 conditions to get this recurrence relation going. You need 4 initial conditions because you're looking back 4 steps here. So you didn't start yourself off with the a sub 4 equal to 2, then you wouldn't be able to start building this sequence. And also we should just note that this a sub n is equal to this under the condition that n is bigger than 4. That's when the condition started to be true. So that's another indication that we need these 4 initial conditions to then start using this fancy equation that we've come up with. Okay, so one more problem for the video. We're going to discuss strong induction. Okay, so in this problem, we're given a recurrence relation. And we're supposed to conjecture a solution to that recurrence relation and then prove it using strong induction. So hopefully this problem will kind of represent the convenience or the niceness of using strong induction. I tried to pick a particular problem that would do that for us. So first, we need to come up with a guess, conjecture this solution. So a sub 0 is 1. And how does this recurrence relation work? You add everything from before, and then you add 1. So it would be 1 plus 1 is 2. And then a sub 3, we would take everything from before, and we add 1. So 1 plus 2 plus 1 gives me 4. So a sub 3 would be 1 plus 2 plus 4 plus 1, which is 8. So we're kind of noticing a pattern here. It looks like we've got 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and maybe that continues on and on and on. So our guess would be that the following statement, P sub n, is saying that our sequence described by a sub n is equal to 2 to the power of n. And this seems to be true. We should quantify this for every n value bigger than or equal to 0. So this is only a guess. It's only a conjecture at what the solution is because we just tried some cases and we're sort of hoping maybe this pattern continues on and on, but we don't have any evidence that it should continue on and on. And that's where induction, or in this case, strong induction, really comes into play. It can verify that our guess is actually correct. Okay, so every time we do induction, we'll need to do a base case or possibly base cases and an inductive step. And for our base case, let's just formally write in that a sub 0 does work here. We do get this equation working out. So therefore we can say that P sub 1, or in this case, it's actually P sub 0, is true. And we might have to come back and do more base cases depending on how we do the inductive step. So in my inductive step, I'm going to show that P sub n is true. And I want to do this for all n values bigger than or equal to 0. But I'm not really sure which steps I'm going to look back to just yet. Before I complete the inductive step, I need to kind of know the plan of, well, how many steps am I going to look back to show that P sub n is true? So we kind of have to work something out before we complete what the plan is. So I want to write a sub n as 2 to the power of n. That's the puzzle that we need to figure out. Right, that's what P sub n says. So I need to prove that. Induction allows me to look at the previous cases, or in this case, numbers that are smaller than n, so n minus 1, n minus 2, and so on. So we get to assume all of those are true. In regular induction, you would just look one step back and say, this statement right here is true for n minus 1. Strong induction allows us to do that and more. It says you can look back more steps if you like. If you're at the nth step and you already know everything before is true, then you could use all that to get the next step in your process of trying to show all these statements are true. So what we can do is write down the recurrence relation that we're given, right? That recurrence relation was just given to us in the problem. So a sub n is equal to a sub n minus 1 plus a sub n minus 2, and so on and so on and so on, right? You add everything from before all the way down to a sub 0, and then you decide to add 1 at the very end. Okay, so now we could say, well, we could use our inductive process on all of that. We can say that all of these indices here are less than n, so we can go ahead and say, this is 2 sub n minus 1 plus 2 to the power, I should say, of n minus 2 plus all the way down to 2 to the power of 0 plus 1. And we'll clarify that this is by p sub 0 and p sub 1 all the way up to p sub n minus 1. Okay, so now for what we have written down on our page, if we look to our lecture on closed forms, there's a nice closed form for a geometric sequence. So we have a geometric sequence here. When we add up the geometric sequence, we get a geometric series. And there's a nice formula to remember in this case. So we have 2 to the power of n, so one higher power than what the largest power is, subtract two to the power of 0, and then all of that divided by the base, which is 2 minus 1. Okay, and then there's still a plus 1 from the very end. So let's just write again. In red, we'll have our substitution that we've made. And if we look through this in nice detail, we do in fact get 2 to the power of n plus 1 minus 1 goes away, and we get exactly what we're looking for in our inductive step. So the only thing that we should sort of return to here is the statement of our inductive step. So we wanted to show that p sub n is true, and we looked back at every single statement before. So we used the fact that p0 is true, and we used the fact that p1 is true, and we used the fact that all the way up to p sub n minus 1 was true. And whenever we're writing n in this case, we should try to quantify it, and it does work for every n value that's bigger than or equal to 0. So that's why this 4 is kind of important here. Okay, but that completes our video for today and completes the problem on strong induction. So thank you so much for listening, and we'll see you next time.